Okay, welcome everyone. My name is Stefan Thiel. I'm the host for today's EMinar. And I'm really glad we've got Kate Brand, who's going to talk to us about MT for lithospheric architecture and mineral systems in Southern Australia. She's chosen a fantastic date and time. It's everything 22s and zeros. So that's really good to see. Let's go to the next slide. Just some information for you about the EMinars themselves. We're actually at the end of series 2. You can see the registration and the actual link to the EMinar website down below. And you can also watch pretty much all of the previous EMinars available on YouTube. There's a link there right next to the registration link for upcoming EMinars. So what I also would like to say that after today's EMinar, next week will be the final one for this series. And that's going to be on the 29th of June. And it's an open mic. It's something that we haven't done before and we'd like to try. It's basically having room for open discussions for 2 hours on any and all aspects of MT and EM. So please make sure you send your questions to the EMinar organizers. And it's going to be all in a Zoom meeting. So hopefully we get enough questions and some good discussion and dialogue going. There's a season 3 in the works already, and that will be starting in around about early October 2022. So if you're interested to give a talk, please send your titles or your topics to us organizers. We really look forward to any content, and the content so far has been great from talks from industry, etc., academia, and also from survey staff. We're coming back to today. We've got Kate Brand. So without much further ado, I'm going to hand over to Kate to share her slides and give a talk.
Thanks, Stefan. Hi, everyone, and good morning or good evening, depending on where you are in the world. And as Stefan mentioned, I'm very happy to give this talk on the 22nd of June, 2022 in season 2 at 2200 UT. So I was pretty amazed by that when I saw it. I'll just get my screen sharing working. Is that all right, Stefan? Yep. And just when I switch screens, I'm not going to be able to see the Zoom window. So just shout out if anything goes amiss because I won't see any typing. All right. Okay, so my name is Kate Brand, and yeah, I'll be talking to you about MT focused on sort of bigger scale imaging, so for lithospheric architecture and mineral systems focused on South Australia. And I'd like to acknowledge many people who have helped in a lot of this work, and I've tried to acknowledge them throughout the talk, but to particularly mention Stefan, Professor Graham Heitzen, Ben Kay and Tom Wise, who've done a lot of work towards these projects as well. So since signing up to do this talk, I've changed affiliations. So if you saw my current affiliation is at the Bureau of Meteorology and Space Weather Forecasting, you might think it's a little bit of a random topic to give my talk on today. So at the time, a couple of months ago, I was at the Geological Survey of South Australia at the Department for Energy and Mining, which is where Stefan works as well. And I'm now at the Australian Space Weather Forecasting Centre at the Bureau of Meteorology and still an affiliate lecturer at University of Adelaide. So the image in the back sort of shows the connection between these two sort of careers that's gradually changing. So you've got the sun, you've got solar wind, and how that's affecting the Earth's magnetic field. So in my previous job, we were measuring those changes in the magnetic field. And in my new job, we're forecasting what's going to happen with the solar wind. So it's really cool kind of coming full circle in that. And just before I left my previous job, this was an image that a colleague, Ursula Michael, made, which shows this variation. So myself upside down on Earth with the MT model in the background, and then MT instruments as satellites. So I thought that was quite clever. So in my talk today, I'm going to talk a little bit, just quickly framing the background of the move towards net zero and why mineral exploration is still going to be very important. And then looking at the mineral system, lithospheric controls and exploration and how MT can help with this, and then give a couple of case studies on this as well. So this image is just showing one specific mineral that's required for the energy transition, which is copper. So for various different technologies that are required for a transition towards net zero, we can see that over a decade, so from 2020 to 2030, we've got gradually as we move along, huge increases in the amount of copper that's required. So for example, we've got with power grids, we've just got a relatively modest increase from 1.7 million tonnes to 2 million tonnes. But for electric vehicle batteries, we've got 210,000 tonnes to 1.8 million tonnes. So that's a huge increase. As you can see that even as we're transitioning towards a greener future, the reliance on minerals is going to be ever more important. This is more general with the middle section is focused on renewable energy solutions, but this graph includes as well just general sort of energy resources, minerals for renewable energies and just other general minerals that are used for many different things in our lives. And what this graph is showing is if you're born in 2010, how much would be left for you using the current reserves at that time. And so the thick lines are based on if production rates continue to accelerate at the rate that they have been accelerating, and the narrow lines are if production rates remain static. So you can see that energy supplies, could run out, anywhere between late 2040 up to, maybe 2100 for coal. With the metals, these are, in the next couple of decades, based on current reserves, would quickly be depleted, and same with zinc, silver, gold and copper. So you can see it's really critical that we continue to keep exploring and discovering new resources. And having a look in Australia, because that's the focus region of this talk, as to what of these resources we have in Australia. So each filled circle represents 10% of the global amount. So you can see in Australia in particular, we've got a lot of uranium, lead, zinc, silver, gold, copper. So, we've got quite a lot of existing resources. So you can assume that, we should be able to find some more. And where have we found these existing resources? So this map shows in general, it's coloured by the thickness of the cover. So about 80% of Australia is under sedimentary cover of some degree. And the circles are the depth of the mineral deposits themselves. So looking at the cover first, so in outcropping regions in orange, that's where we're going to be finding most of our deposits, and in yellow where there's less than 500 metres of thickness. And so you can see with these white and yellow dots around, you can see that's where most of these mineral deposits have been found. But when we're looking at the blue and the purple deposits, you can see here that we've got a lot less of these, and in general they're much bigger deposits, because to be able to find them that deep, we need a relatively big signature. And this image, this is just a depth slice from AusLAMP at 2 kilometres, which is probably a big no-no given that the site spacing is 50 kilometres apart, but it is just quite a cool image that shows the red conductive sediments and the mineral occurrences of gold and copper in South Australia. So you can see that these, again, as we saw in the previous graph, these are all occurring in these outcropping regions. So why are we only sort of seeing in that shallow cover region? On the left of this, outlined in the green rectangle, we've got the sort of more traditional exploration techniques. So from mapping, geological mapping, drilling, which is quite shallow and expensive. We've got potential field methods, magnetics, gravity, reflection seismics, again, really quite expensive. And so with those methods where we might be sort of penetrating through the barren cover, but it can be difficult to get to those mineralized rocks. So luckily for us, these mineralized rocks are often associated with deeper pathways. So it's up to us to try and work out how to visualize these. So for that, we can use what I've referred to as the bottom-up deep imaging techniques. This map here is showing, these various different regions where we might see these deeper signatures. So we've got on the left, we've got subduction, and we've got an arc region, which is prospective for copper porphyry deposits, and you can have associated fluids and melts from the subduction back arc regions with magmatism VHMS deposits, and in orogenic regions, orogenic gold, associated fluids and conductive mineralogy with that as well. This map here is showing a lithospheric thickness across the globe from a study by Hogarth et al. In 2020. So we've got the thinner lithosphere in red, the thicker lithosphere in blue. White is kind of that transitional region with lithosphere at about 170 kilometres thick. And this 170 kilometres was found to be quite significant in this study. So plotted on top is global deposits of SEDEX deposits, so lead, zinc and copper sedimentary deposits. And 85% of these deposits around the globe occurred within 200 kilometres of any of these 170 kilometre thick lithosphere regions. So within 200 kilometres of all of the white parts of the lithosphere here, that's where we're finding 85% of those SEDEX deposits. And also all giant deposits within this study are within that region as well. So not 85% for the giant, it's 100%. So this is just one data set that's showing how the lithosphere can have huge controls on the locations of mineral deposits at the surface. And the time frames for these deposits, the scale shown down here is anywhere from 2 billion years ago. So this is something that can be retained over a huge amount of time. And this is just zooming in on Australia, just another image taken from the paper. So this is the western 2/3 of Australia is sort of the older region of Australia, and the east is the younger region. And as we've got that sort of transition from the thicker lithosphere to the thinner, this is where we've got a lot of bad sedimentary SEDEX deposits. And so we can use various different tools to try and get these deeper understandings. So we've had a look at lithospheric thickness. We can get geochemical data from various different sources, seismic tomography data, and magnetotellurics, which I'm sure you've guessed is going to be the focus of this talk. So finding a mineral deposit is obviously very difficult, and mainly because it is just such a small thing that we're looking for. So, but if we look at this mineral deposit in the where it sits within a greater mineral system, that's when we have a greater chance of being able to actually see the signatures associated with it. So you can see here we've got you've got your ore deposit, which would be very difficult to find, but you've got this much bigger fluid delivery pathway that can extend all the way down into the bottom of the lithospheric mantle with heat, fluids and metals that can be sourced from as deep as the asthenosphere. And so we've got on the right, we've got broadband MT, long period MT going down into the mantle, both great tools for being able to image this. And we've got in South Australia this kind of world famous example. So Olympic Dam is the world's largest uranium deposit and the 4th largest copper deposit. It's an iron oxide copper gold uranium deposit. You can see it's got this conductive pathway heading up from this really deep conductor. It's been dubbed the fingers of God. And we've got 2 other fingers going up from this conductor here, one to Werder Well, one to Vulcan, so 2 other IOCG deposits as well. So just very briefly looking at the geology of Australia. So I mentioned we've got the western 2/3 of Australia, which is the older part. So we've got the North Australia Craton, West Australia Craton, and the South Australia Craton. So the darker regions are the sort of smaller cratons that make up that area. We've got various sedimentary basins throughout and orogenic regions through the middle. On the east, we've got the Phanerozoic part of Australia. So this is what's called the Tasmanide. So that's a series of origins that have accreted onto the eastern edge of Australia, starting from about 510 MA and gradually progressing then. So this is the area that we're mostly going to be focusing on for my talk, outlined in green. And in red, so we've got here the Gawler Craton, and we've got the Kernamona province here. So it's thought that these two regions were connected prior to rifting, where we now have the Flinders Ranges in between. So the Gawler Craton hosts the vast majority of South Australian mineralisation, so that's quite significant. So we've got, across Australia, we've got so much different geological, geoscientific information that these are just, you know, a small assortment of some of these maps, potential fields, geology maps. We've got a huge number of water bores, seismic lines, geochemistry. Where do we sit with conductivity? So this was, I guess, where we began in terms of having a national conductivity model. So this is from the AWAGS survey, which was collected several decades ago, just using geomagnetic depth sounding data. So I'm sure you're all aware that that's not as good as constraining the conductivity as MT data. We can't really get the depth of conductivity features, and we also can't constrain very well the absolute conductivity. And the site spacing for these GDS sites was around 400 kilometres as well. So it's very low resolution. So these black triangles, just ignore them for now. They're AusLAMP locations, so not the data that we use to create this model. So the next step from there was, how do we increase the resolution of this map? And that's the Australian Lithospheric Architecture Magnetotelluric project. So this is now in about its 9th year, and it's around halfway complete. So the pink and the red dots have been completed. And the dark blue, black dots are still to come. So you can see we've made pretty good progress, and once complete, there'll be 2,800 long period sites. So Stefan talks a lot about this in his EMinar, so I encourage you to check out the results, a lot of different results from that in his talk as well. So it's a very collaborative project, so between Geoscience Australia, state government agencies, universities, University of Adelaide, other universities as well around Australia. So by all working together, we've made great progress so far. Of course, this is not a great way to look at all the models together, and it just took me a couple of minutes, and if only modelling such a large area would be that easy as to just sticking some different images together. But I just wanted to show you the areas that have been modelled across Australia, and there's probably a few sort of smaller models as well. But you can see that we're getting a huge increase in resolution, and when we sort of move towards doing an inversion of the whole area together, that'll be a really great map set that we'll be able to add to these sort of national maps. So AusLAMP has involved a lot of field work, which has been, a fantastic experience. And these are just a few of the many happy snaps that have taken along the way. We've got our famous Sturt Desert P. We did a lot of helicopter field work going over the Flinders Ranges and nearby mountains. And it wasn't all smooth sailing. So on the right, you can see the amount of flies that you get in the bush. Wearing a fly net is a must. And sand dunes, getting across the Simpson Desert, we had heaps of different sand dunes to cross. I think it's several hundred. And doing that in a truck is no easy feat, but it was a great experience. And just to give you a bit more of an overview of what sort of a lot of the country looks like, so sort of low dunes and very scrubby. Not too much to see, but it is very beautiful. And we'd access a lot of the sites using a helicopter because there's not roads that just happen to visit every half a degree across Australia. So now we've got, this is a bit of an earlier map, so it needs to be added on. We've got more data around here and up here, but this is just focusing on some of southern Australia, looking at induction arrows at 1,000 seconds, so in sort of the upper mantle depths. This is Parkinson convention, so pointing towards conductive regions. You can see we've got the Gawler craton, which is a really old resistive craton. It's got this pincushion effect where all the arrows are pointing out. We've got the Musgrave Paleoproterozoic origin, and the boundary sort of around the Gawler craton. And you can see arrows as well pointing towards the ocean, so just the coastal effect there. I'm not going to talk much about this at all because, as I mentioned, Stefan's given an excellent talk on AusLAMP. These are some images from his work, but just very briefly, so looking at a couple of different depth slices, so 16, 30 kilometres and 58 kilometres. I think in particular, the correlation really stands out at 30 kilometres, where you've got these high conductivity regions coming around here. So this is where we had the sort of pincushion arrows were sort of pointing out towards this conductive boundary, and this is where you've got IOCG deposits and prospects occurring down along at the surface over these regions. So here we're seeing, you know, at 30 kilometres, a conductor that's associated with mineral deposits at the surface. So now I just want to move into a couple of case studies. So to start with the Delamerian. So this was a collaborative project done by the Geological Survey of South Australia with Geoscience Australia and support from the University of Adelaide and instrumentation from AusCope. So the Delamerian origin, it's a bit of a funky shape. Outlined in black is the area that's been impacted by the Delamerian origin, which occurred about 515 million years ago. We've got the Flinders Ranges through here. This is Neoproterozoic, the Gawler craton, the Curnamona province, and then one of the next origin in the succession of the Tasmanides, so after the Delamerian origin. And this part, so we've got this arcuate shape here. This is Nakara Arc, named for its arcuate shape rather than it being a volcanic arc. And we've got these various packages built. The Lochbilly Karst Belt, which this red line is going to be a region of interest for us that we'll talk about shortly. And over here, we've got a region that's covered by the Murray Basin sediments. This is a region that's particularly unknown as well. So starting from 800 MA with the breakup of Rodinia, there was passive margin rifting. So this was from the Neoproterozoic to the early Cambrian, and there was associated sedimentation, which resulted in the Adelaide Rift complex that forms most of the rock of the Flinders Ranges today. At 520 MA, we had the initiation of subduction indicated by bonaninic magmas that were found in Victoria and South Australia. We had back arc extension occurring and associated magmatism in South Australia, and oceanwood trench retreat into Victoria. Then we had subduction fully underway, 515 to 490 MA, with this westward dipping subduction into South Australia. So for context, over to the west would be the Gawler craton there. And of course, a lot of magmatism associated with the subduction. And then 495 to 470 MA, we had slab break off and the slab steps back outboard. A lot of magmatism occurring, exhumation, delamination. Pretty complex story. So now having a look at the model. So we performed a 3D model, well, lots of 3D models. This was this one, our preferred model using ModEM. This is a 20-kilometre depth slice of that model. So you can see it's a little bit splotchy, but there's really major conductivity features coming out. So we've got this air peninsula anomaly, which we'll talk about a bit later. The Curnamona province, which is hugely conductive, and Graham Heinsohn's given a good EMinar on this. Ben Kay's done a lot of work on this, as well as myself earlier on. But our region of interest that we're mainly going to be focusing on, sorry, I just realised my cursor was on the wrong screen. Our region of interest is going to be mainly along here. And so just because you couldn't see where I was pointing before, this is the Eyre Peninsula anomaly we'll talk about after, in the Curnamona province that Graham's talk was on. So this is looking at a depth slice of 40 kilometres for the model. So we're going a bit deeper now. We're probably into the shallow upper mantle or bottom of the crust. And again, this is the feature that we'll focus on for the talk, but you can see it's really long, over hundreds of kilometres, and sort of curving around. So we're into New South Wales and Victoria. It's quite a lot of interesting features down here, but this is work that Alison Kirkby has done. So she's got a few talks and papers available on work down there as well if you're interested. So on the right, we've got a 50-kilometre depth slice, and I've got copper and gold occurrences plotted over top in yellow and gold. So yellow for gold and orange for copper. And you can see that by and large, these are all occurring where we've got these deep conductors. So I should point out that these are just occurrences rather than deposits. So sort of any sign of copper or gold would allow one of these marks to occur, as opposed to actually finding a resource that's economical. If I now add a geological image with outcrops, so this is the outcrop of the Flinders Ranges into the Mount Lofty Ranges, and you can see this curved feature down here, and that's where the continuation of these copper and gold occurrences are. So most of these are occurring down here. So probably what we were expecting is that we would see the conductive anomaly extend down along that area, but instead what we're seeing is it sort of takes this bit of a tweak around here, and that jumped out at us as being quite interesting. If we now plot, rather than just looking at occurrences, we plot deposits. So yes, there is a deposit down here, Kaman-2, which is where the curving around is, but we've also got one here. So this is Hillside. This is an iron oxide copper gold deposit. So this is Mesoproterozoic. It was associated with the intrusion of the Hiltebus suite. And so that was, 1595 MA. Moving along, we've got Burra. So this is Neoproterozoic to Ordovician. This is porphyry copper. You can see this scale up here as well, the legend. And then we've got Anabama Wadnaminga. So this is copper gold, copper molybdenum, gold deposits around here, and a lot of porphyry style as well. And then we've got Broken Hill. So this is different again. This is lead, zinc, silver, SEDEX deposits, 1.8 billion years old. So you can see we've got this one major conductor that seems to connect these various different mineral deposits, and with significant differences in age. So occurring from, around 1.8 billion years ago to perhaps as young as, 400 million years or so. We've got, I mentioned there was subduction and sort of back arc regions. We've got a lot of these sort of back arc regions in South Australia, so highlighted in green on this image, and this is our area of focus. So we've got back arc signatures here, and going into the back arc region, this is where we might see VMS deposits. Whether they would have any sort of conductivity signature associated with them, something we could find out with a bit more detail as well. So we collected 66 broadband MT stations along, just to go back, show you again, so 66 MT stations along this line with 1.5 kilometre spacing. So that's a huge increase. So on the left, we've got an extract from AusLAMP, an AusLAMP model, which is 55 kilometre spacing. Ignore the triangles at the top, that's for the wrong sites. And then on the right, we've got the broadband data. So this is 1.5 kilometres. So both 3D models, but hugely different site spacing. And on the left is long period, on the right is broadband. So you can see we're seeing some similar trends, but also some differences. But overall, the most astounding thing is just the increase in resolution. So it's a very worthwhile endeavour. You can see one particular region of difference is here, where we've got this resistive region between these surface conductors, which match quite nicely, these C1, C2, C3, and then this connection to C5. And so we've done quite a lot of testing as to whether the continuity of these shallow crustal conductors down into the mantle is required, and it seems that the data does require this. So this is just something that obviously wasn't being able to be resolved just from the AusLAMP data alone. We've got a couple of features we'll talk about more later. The Anabama Pluton, which is really resistive here with these sort of conductive pathways going around it, and Anabama Red and Shear Zone, which comes up as conductive in this otherwise really resistive subsurface here. And if we also did a 2D inversion of the data as well. despite the fact that the data had a lot of three-dimensionality to it. So for that reason, I've only shown the depth slice to 2 kilometers because it's mostly 2D in that sort of depth region, and this has got a huge vertical exaggeration of 20 times. So here you can see, I mentioned that the southeastern end of the profile was impeded with Murray Basin sediments, so it made it difficult to see anything underneath. So you can see these come out nicely here, and we've got this really resistive pluton and various different conductive features here. So you can see, so here we're in sort of the Flinders Ranges and Nacra Arc region, the Neoproterozoic rocks, and then we move into the Loch Lilly Karst region where we've got more Cambrian rocks. And this pink section is the Anabama pluton. You can see it heading into the plane there. So this is just taking a quick look at the model in 3D to put the context of the broadband transect in a bit better context. So looking at a depth slice, and we've got some various mineral occurrences, mineral deposits, in green, and I've turned on some conductive isosurfaces, and then turned on some resistive isosurfaces. So when we turn off the background, you can see this clearly. So you can see that this profile is along this long pink band here, so the conductive band. We'll just zoom in so you can see that a little bit better. So this is that long conductor there. So you can see half it's on it, half of it's not, as we've seen in the previous images. Okay, so looking at these two models combined, so this image shows the AusLAMP isosurfaces from the AusLAMP model, but also isosurfaces from the broadband profile. So using 50 ohm meters for the conductive and 5,000 ohm meters for the resistive. So you can see this is part of that really long conductor, which we've called the Nacra conductor. So that continues along in this direction. And then we've got these pathways that are coming up. So we've got the conductive sort of mantle source, and then we've got conductive pathways in various regions. And you can see here, this is the Anabama pluton, and the shape of these isosurfaces, I think, give quite a good indication that it seems like this pluton would have been emplaced prior to these conductive pathways forming. So that that's really useful for giving some timing constraints on these conductive pathways as well. You can see the conductive sediments here. So colleague Tom Wise has done a sort of cartoonized version of this model. There's a lot of detail, you probably don't need to take it all in, but you can see, here we've just got the mantle source and the conductive pathways. And the cool thing is that we've got these deposits at the surface that are in locations sort of just above or near where these pathways come up. So we've got the Anabama pluton, the granodiorite pluton, that was the really resistive region. And then we've got copper, gold, molybdenum along the edge of this. We've got copper, molybdenum porphyry deposit, copper, molybdenum here. And then over with this other conductive pathway, we've got gold. This is 10 kilometers along strike, but we've got vein hosted gold. And fluid inclusion studies show that these deposits here and here have come from the same sort of mantle source. So it's really cool to be able to sort of image that system fully in 3D. And also as well, help to provide some timing on those mineralization fluids. So just to move on to the next case study. So just checking how I'm going for time. So we've done some work on the Eyre Peninsula and in the Spencer Gulf. This was a collaborative project with the Scripps Institution of Oceanography, the University of Adelaide, who led the project, AusScope, who provided some funding and instrumentation. Funding, Geoscience Australia and the Geological Survey of South Australia. And that was the ship that we used to collect the data, and you can see the instruments on board there. So we collected 12 marine MT stations across the Gawler Craton, and we had the sorry, ignore that comment. So we collected 12 marine MT stations across the Spencer Gulf here. And we had as well, a little bit earlier, some land MT sites across this transecting green. And the yellow dots are showing the AusLAMP sites. We actually had to change our plans. It didn't get to collect the gridded black triangles. And these are some earlier data that were acquired several decades ago. So marine MT was all new to me. Perhaps there's some people listening who it's not new, but there was a lot of things you had to consider that you don't have to for land MT. So I'll just touch on those briefly for anyone who's interested. So timing was particularly important. So when is a good time with the tides and currents? Learnt, we had to look at this tide predictions and work out a time when you're going to have the lowest tide. So what's called dodge tides. So we picked our window. Unfortunately, it coincided with the COVID lockdown window, so that had a little bit of trouble where we had a couple of people have to stay in lockdown in a hotel room for a week or so. We had shallow water depth, so there was some changes that need to be made for the instrumentation because we were looking at 40-meter water depth. We needed a lot of space and time to be able to prepare the gear before we went out. We had to worry about fishing seasons. There's a lot of prawn fishing that occurred. And for a lot of really useful information about the logistics and anything to do with marine MT, Steve Constable has a paper, Geophysical Prospecting, which is really good. And he's also done an EMinar as well, so worth having a look at that. So this is the ship that we use. You can see we've got a crane to lift the instruments off the side of the boat. They're very heavy. They've got a concrete anchor on the bottom. And this is just a sketch from Steve Constable's paper that shows what the instruments that were designed at Scripps looks like. So you've got glass flotation spheres to bring it back up to the top afterwards. You've got the magnetometers, BX, BY, and you've got the electric dipoles, which are these sort of long PVC pipe, which you can see back here, that have the wire in between the pipe. So that's sort of a close up on those pipes there. And I think they were around 4 meters or so, but usually for deep marine MT, I think they'd use about 10 meters. They'd have a much bigger ship in that case, so they could actually fit those tubes on the ship, which we could not on our deck space. And then these are the electrodes that we were using. So this is just a time lapse of setting up an instrument. So putting on the arms, putting the magnetometers in, getting the GPS set up, the acoustic signaling. So you send an acoustic signal when you want to, for a burn wire to operate, and this releases a buoy that floats towards the surface and means that we can actually pull the instrument back up afterwards. Otherwise, it would be a bit hard to get these from the bottom of the ocean if that process didn't occur. So that's pretty critical. So it only takes about 15 minutes to set them up once you're actually on the ship. It's the work prior to getting them onto the ship, I think, that takes a long time. Personally, I found it a bit easier than land MT, because you just threw it over the side of the ship and you were done with it. There was no digging of holes and trying to dig through rock. So I very much enjoyed it. So just a couple of other quick videos. This is one just, we kind of try to keep it stable. And then as we put it into the water, you've got a quick release on the crane, and then it sinks down to the bottom. Then we had some lovely sailing, and it was very peaceful for parts of it. Then you had other parts where, perhaps if you're used to being on the ocean, this might not seem too rough, but for me, this felt really quite rough. So they were the points where I thought, okay, I really do appreciate land MT. But yeah, it was definitely a great experience. So very grateful for Scripps' support as well to be able to enable that to happen. So the geology of the area that we're looking at, so we're looking at the Spencer Gulf down here in this red region. The Gawler Craton, takes up a large portion of South Australia, and we're looking at the very sort of southeast corner of that. We've got the Air Peninsula, which has a series of subparallel complexes that are bounded on the east by the Kalinjala shear zone. This is 1790 to 1740 MA feature reactivating the Kimber orogeny, which is thought to have reworked an existing boundary. So it's a really old, significant lithospheric scale feature there. Then we sort of transition into the Gulf, and then we've got the York Peninsula on the other side, which has rocks of the Hiltova Suite, which you see up here as well, where we get a lot of the IOCG mineralization associated with it. But then in this more detailed image of within the Spencer Gulf, you can see the sites that we managed to collect in yellow over TMI data. In orange here, this is just a solid geology map. So in orange, sorry, we've got in pink the Spilsby Suite, and we've got the Donington Suite in orange through here, and the Hiltova Suite here. So looking at it in terms of conductivity, what did we know beforehand? So we've got the AusLAMP model across the area, as we do across most of the state. We've got this really conductive air peninsula conductivity anomaly, which seems to be bounded on the east by the Kalinjala shear zone. Doesn't seem to extend into the Spencer Gulf, but worthwhile collecting data in there anyway. We've got, this is kind of the foot of that major conductive feature that we were talking about in the previous case study, and then various conductivity anomalies that sort of snake around the Gawler Craton. So there is actually quite a large amount of MT data across the area, just from various studies over time, because this feature was identified 3 or 4 decades ago. It's very old, one of the earliest identified resistivity features within Australia. So looking at the induction areas again in Parkinson Convention, you can see they're all pointing towards this major anomaly, and it seems to sort of extend into the ocean a bit as well. We've got a new MT profile sort of roughly across here or so, that was work done by Ben Kay, Lachlan Loader, Graham Heinzen, and a few others, myself and Stefan. And so from there, we could actually image what the Air Peninsula conductivity anomaly looked like. And so you can see that it's most conductive near the surface, so sort of 5-10 kilometers depth, where we're looking at, really conductive, sort of more conductive than seawater. And then we've got it connected to this bigger, much broader feature, which is still conductive. Here we're all looking at less than sort of 20 ohms, but obviously nowhere near as conductive as C1. And so this location here is the location of the Kalinjala shear zone. And in red and yellow, we've got graphite. One is a graphite mine, one's a graphite prospect. This and a number of other things have sort of led us to believe that this is graphite near the surface, and also that has been exhumed during the orogeny that occurred around 1.7 billion years ago. And this, as well, we expect graphitization to have occurred throughout the whole area, but with a lower level of exhumation occurring, sort of sitting there in situ, it seems like it's stayed a bit less conductive. So this is just a cross-section of the AusLAMP model through the area. So the modelling, so this hasn't included any of the Spencer Gulf data, but the modelling of the Spencer Gulf data is still a little bit quite preliminary at this stage. We ended up reprocessing the data to correct for a few different things. So that's a bit of a work in progress, but I will show you just where we're at the moment. So you can see from AusLAMP, we see the air conductivity anomaly, and this is the southern tip of the nacre conductor that I was talking about in the previous case study, and the resistive, really resistive igneous rocks of the Donington Suite here. And then doing a 2D model using Murray 2D, now incorporating the broadband transect and also the marine MT transect. You can see that we're getting a little bit more detail starting to come out, and I suspect once we run this model again with the improved data, because we had to mask a lot of data with the initial processing, that we'll be able to get much better constraints. But you can see it definitely looks like the air conductivity anomaly doesn't continue under the Spencer Gulf, and when we can sort of see the extent of the Donington Suite as well coming out from that. And again, it does seem like we're imaging to the southernmost extent of the Naka arc conductivity anomaly, and that it doesn't tend to continue further into the Spencer Gulf. Sorry, just skip over this. So yeah, it's, as I mentioned, it's a work in progress, and we are in the early stages of doing some 3D modeling of that whole area, which I think will be really fascinating using the 3D code from GeoTools. So stay tuned for results on that. And I think with that, I'd like to wrap up. So just to reiterate, focusing on the full mineral system can help us to explore undercover. And magnetotellurics is widely used in Australia by government, by academia and industry. So we do this kind of in a scaling way. So we start big with AusLAMP, then we work out areas of interest, then we might do a broadband survey, and then usually at this point, that's when industry might jump in and do a higher resolution broadband or AMT survey to get that sort of those final details to the picture. And so in order to be able to work out where to focus these further studies as well, we do need to keep chipping away at AusLAMP. And then as well, you know, getting that really large scale benefit of having a map of all across Australia. So there are a lot of people to acknowledge, so I won't, I'm sure I won't manage to name everyone, but thank you to anyone who helped contribute to any of this work. The various different geoscience agencies that have contributed data, logistical support, funding. Modelling was usually done using the NCI's supercomputer, using a grant for that. And then very much appreciative of all the open access software that's been utilised throughout this and other work. So MTPy, 3D Grid, Mari 2D, generic mapping tools. And of course, we'd like to thank AusScope for the instrumentation and the traditional owners and the landholders, without which their permissions to access their land, we wouldn't have been able to collect any of this data. So thank you very much.
Thank you, Kate, for the talk. That was fantastic. I think it's always astonishing to see how well the correlations kind of stack up, you know, with known mineral occurrences and MT conductors once you conduct the infill-survey. So that was really good. We've had one question coming through so far. Please, if you have other questions, pop into the Q&A at the bottom, and we'll get to them. There's one fairly general question by Cornelius Amurtang, and this is, please, what is MT modeling? So I think this is a question around, I think when you started talking about the marine surveys, you know, really what do you, or what do we mean by modeling? What does that entail?
Okay, yep. Yeah, so I guess I'm using, by modeling, I'm interchanging that with the word inversion. Perhaps that's a bit sloppy, but basically, so we're acquiring the raw data, we're processing up that data, so we acquire it in the time series, then we do the processing to get it in the frequency domain. We've got these isolated locations where we have data about the impedance of the Earth, but what we want is to be able to put that into the broader context. So that's where we perform the modeling, so I guess all of the results, you know, apart from probably the induction arrows today, are the results of modeling. So we can do that in 1-dimensional, 2-dimensional, or 3D modeling. I'd imagine there's some pretty great EMinars on this, but it's about, yeah, taking those independent measurements and putting it into that 3D or 2D or 1D sort of actual model of the conductivity.
Okay, that's great. There's another question here that I think they would just like to get her your email for further question, but I think we might do that offline.
Yeah.
Rather than mentioning that here. But yeah, I think if you want to get in touch with one of the organizers, we can forward the email.
Yeah, I can also just type it in the chat right now, I think.
Perfect. Yeah.
So,
yep, that's good.
I'll put it in the chat there. So.
Yep, thanks, Kate. Yep, if you have other questions, please pop it in. In the meantime, I might just have one, Kate. So I think, I mean, AusLAMP itself, you know, has shown sort of in the big picture how well that really matches the mineral systems in Australia. Has it helped you guide precisely where you want to do the infill surveys? Or in other words, if you didn't have AusLAMP, do you think you put the infill surveys where they were, or has it helped you really hone in on one area much better and save some money? Or what do you think is the value for AusLAMP for designing the infill surveys?
Yeah, I think it's really valuable. I'm thinking about most of the subsequent studies that I've done since AusLAMP. We've had AusLAMP in South Australia, and I'd say almost all of those have had the locations sort of heavily influenced by the AusLAMP conductors. So it's not to say that we wouldn't collect a profile over a region that's resistive. And you saw in the Delamerian example, the profile that we collected, that was in a particularly interesting region where we had the transition from something that was hugely conductive to hugely resistive. So, we had that transition into the back arc region, which, has probably had a lot of magmatism in the past. And as a result, we're not really seeing too many conductive features. So I think we're using it all the time. I say we, but I guess me not anymore since my new job, but at the Geological Surveys, Geoscience Australia, to pick an area that is interesting, where we've got existing geological questions, but we want, as well to know that we're going to get something out of it with the conductivity. But then as well, I think companies are using it too, so they might see these AusLAMP models and these connections to mineral deposits near the surface, and then take that opportunity to get the smaller scale surveys. I mean, it would be impossible for them, to be able to cover areas anywhere near as large as that. So the work, I guess, being done by geoscience surveys and universities is really important for that.
Thanks, Kate. We don't have another question yet. I'll just give it one more shot, but I'll have one final question. You did mention that you have to be quite careful of when you acquire marine data. And in the end, was that then reflected in the data quality? You showed some models, but what was the data itself like? Can you highlight that a bit?
Yeah, I think a little bit. So in the end, I mentioned the COVID lockdown, so that meant we only managed to keep the data out, the instruments out for a couple of days, which sort of significantly degraded the quality of the data. It meant that we had to try various different things with processing. So Steve Constable ended up processing the data, and since then, we've got significantly improved responses, but have not yet had an opportunity to put those into a model, although we've got the 3D modeling underway. So I think while we did well picking a dodge tide, having the COVID lockdown and the shortened amount of time that we could leave the instruments out, which was very much out of our hands, but yeah, that's what I guess caused the impact. But the dodge tide, I believe, did help.
Great. Yeah, thanks, Kate. We're getting a lot of thank yous coming through. So people who were online really enjoyed your talk. So thank you again for your time. There's no further questions, so I might leave it at that. And just kind of general mention that, please tune in for next week's open mic. And we'll might leave it there. But again, Kate, that was really good to see the results coming through.
Thanks for hosting and getting up at midnight to host the talk.
Yep.
So,
No problem.
all right.
Yep. Thank you.
Everyone.
See you, everyone.
Bye.